Hi everyone, my name is Ten Möllering and together with Adita Hedge, I will present you our systemization of knowledge on efficient privacy-preserving clustering. This is joint work with Thomas Schneider and Hossein Yalameh of the Encrypto Group of the Technical University of Darmstadt. So first I will give you some insights into the motivation and preliminaries of our work before giving you details of our survey of in total 59 private clustering protocols. Afterwards, my colleague Aditya is taking over to present our evaluation of 4 state-of-the-art private clustering protocols and concluding with the challenges that we identified for private clustering in real-world applications. Clustering is an unsupervised machine learning technique that groups similar items into so-called clusters, while different elements should end up in different clusters. It has many applications ranging from the financial domain into the healthcare area. For example, it can be used in the detection of credit card frauds by businesses for market segmentation, allowing them to identify target customers that can be addressed with similar marketing measures, as well as for medical imaging. All these applications involve highly sensitive information calling for private clustering schemes. We, in our work, conducted the first comprehensive review of 59 private clustering protocols and compared them with respect to multiple aspects such as clustering quality, privacy leakage, and efficiency. Further, we give a guideline on how to choose an appropriate clustering protocol given a concrete application. And finally, we also experimentally compare 4 state-of-the-art private clustering protocols with respect to quality and efficiency, and also open source our implementation. What you can see here now is an overview of the results of the 59 private clustering protocols that we analyzed. What actually does private clustering, or even better, fully privacy-preserving clustering actually mean? So let us consider a trusted third party where multiple parties, data owners provide their data to, and this trusted third party then does the clustering and will return the output either to the data owners or to another party. And this is what actually also should be reached by fully privacy preserving clustering. It should not leak anything beyond what can be inferred from the output, such as if we would have a trusted third party. And we identified 4 requirements for such a fully privacy-preserving clustering scheme. The first aspect is, of course, privacy. So we want to have this fully privacy-preserving property, as if some intermediate information is leaked, it is difficult to understand what this implies. So what kind of information is actually, if we would have very special constellation of data. Then we, of course, want to have efficiency with respect to communication and computation as well as memory. We want to achieve a good clustering quality, and ideally, we also want to have the flexibility for different scenarios, such as outsourcing, where one or more data owners outsource the data to a third party, which then does the clustering or as well as the storage. And this can, for example, be a cloud server. Then, of course, we also want to have the possibility to do multi-party computation directly between the data owners. Okay, now we look at our survey of these 59 private clustering protocols. We identified in total 7 aspects that help us to understand for a concrete application which private clustering protocol might be the best fit. So the first aspect is, of course, the plaintext algorithm. No algorithm is superior to the other algorithms. So there are always aspects in which one of them is better than another, and there's no such algorithm that is the best out of them. And in total, 8 different clustering algorithms were kind of translated to a privacy-preserving variant. And we compare these with respect to the strengths and weaknesses in our paper. Then we also look at the security models, and most of the works, except from 3 actually, focus on the semi-honest security model, and only 3 look at malicious security as well. Then there are works that look at outsourcing with 1 or more data owners, or at 2-party and multi-party computation. Some also consider both. Further, these protocols differ with respect to the data partitioning, so some assume that the data owner holds complete data records, while others assume that they just have some parameters of the data records, or they have even the possibility to have an arbitrary data splitting. Different techniques for achieving the privacy-preserving property were used. many use homomorphic encryption, some do public key cryptography. Then there are also a few that look at multi-party computation with, for example, garbled circuits or arithmetic secret sharing, or a mix of these techniques as well. Then, as already indicated, only a few works, actually only 10 works, achieve fully privacy preservation. The others leak some kind of information in between, and we also categorize this kind of information that is leaked there. And finally, the efficiency property. We, of course, want to have a computationally communication efficient and memory efficient protocol. And we also look at these aspects in our works when we categorize the different protocols. What you can see here now are the only fully privacy preserving schemes that we identified. So most of them are using the k-means algorithm, and a few are also done with dbScan, affinity propagation, mean shift, and hierarchical clustering. However, we also looked at the efficiency property here, and especially the old works mostly have used the Payet encryption scheme without any optimization, such as packing or parallelization, which makes them slower than the state-of-the-art works. And we identified 4 of them to be the fully privacy preserving and most efficient. And as they were not directly compared to each other, we conducted this comparison. And this is where I hand over to my colleague Aditya Hatch, who will give you some insights into our experimental comparison of these protocols.
Thanks, Helen. We benchmarked the runtime of the state-of-the-art secure clustering protocols on a collection of small datasets. For computing the clusters on the largest dataset in this collection over LAN, the multi-party computation-based k-means protocol of Mohasel et al. Was the most efficient and took 25 seconds. While on the other end, the fully homomorphic encryption-based mean shift protocol of Kian et al. Took 1.7 hours, which is around 240 times more. And the increase in runtime was mainly because of the overhead of fully homomorphic encryption. Over WAN, the runtimes of all the protocols except that of Kian et al.'s HE mean shift protocol increase, since the remaining rely on MTC and have multiple rounds of interaction. Interestingly, the change in the network setting leads to the runtime of the hierarchical clustering protocols of Meng et al. To be higher than that of HE mean shift. Once again, the MPC k-means protocol of Mohasel et al. And the privacy-preserving dbScan protocol of Bosdomir et al. Are relatively more efficient and have runtimes of around 20 minutes. For evaluating how the protocols scale to larger datasets, we benchmark the performance of the protocols on a collection of large datasets described on the right. Unfortunately, the memory consumption of the privacy-preserving dbScan and the hierarchical clustering protocols was too large on these datasets for benchmarking. The MPC k-means protocol had a runtime of around 5 hours, while the HE mean shift protocol had a runtime of around 23 hours in this case, which is around 5 times more. So the impact of the computational overhead of FHE decreases for large data sets, since the communication cost of the MPC-based protocols also increases significantly. The large difference in the runtimes of protocols means that the choice of protocol in practice is often decided by the performance rather than the underlying clustering algorithm or any other aspect. We also evaluated the clustering quality of the protocols on datasets with different parameters like number of clusters, density of clusters, outliers, noise, and so on. The main takeaways are that the clustering quality changes significantly with the protocol or algorithm, and no algorithm works well on all datasets. In general, we found that dbScan performed well on most datasets, while k-means usually worked on convex and linearly separable datasets. Moreover, the clustering quality was strongly influenced by the value of the parameters, like the number of clusters in case of k-means and the neighborhood radius in case of dbScan. These values depend on the input data and require a bit of trial and error in setting the optimal values. Finally, the clustering quality of protocols like Kian et al.'s HE mean shift varied significantly with the randomness used. That is, its output quality wasn't consistent and had a strong dependency on the initialization. The impact of randomness was lesser in other randomized protocols like Mohasel et al.'s MPC k-means, which uses local computation by data owners on their datasets for better initialization during the protocol execution. We now discuss the challenges in applying secure clustering to real-life applications, and future research directions to make secure clustering more practical. We believe the best way to understand the current challenges to secure clustering is to compare it with the workflow for plain text clustering. Ideally, we would want secure clustering protocols to be as easy to use and apply as their plain text variants. Consider a user which wishes to cluster a dataset. Since this is the plain text scenario, the user has access to the entire dataset and moreover, they can visualize and analyze it. Now, this makes it easy for the user to select an appropriate clustering algorithm and its parameters. For example, in this case, the user might learn that the dataset consists of 4 clusters that have a simple spherical shape, and they might decide to use k-means, which usually works well on such datasets. The user obtains a possible set of clusters after running the algorithm, which can then be evaluated visually or by computing internal clustering indices like the silhouette index, which helps quantitatively compare different clusterings of the dataset without requiring any ground truth. Now, as we see in the example here, in some cases the output might not be of good quality, either due to bad initialization or non-optimal parameter values, in which case the user reruns the algorithm with different parameters and random seeds or on a completely different algorithm. Finally, they can evaluate and select the best output. Now let's look at the challenges that arise when using secure clustering protocols in a similar workflow. In this case, the dataset is distributed among multiple data owners that wish to cluster on the combined dataset. As mentioned previously, no algorithm performs well on all datasets. Moreover, the protocol parameter values have a significant impact on the clustering quality, and the optimal value of some parameters depends on the input data. Since the dataset is distributed among the data owners, there is no easy way to perform a preliminary analysis on the combined dataset. Now, this makes it hard to choose a suitable algorithm and its parameters. Also, since the performance of protocols varies significantly, the choice of protocol might depend on the efficiency of the protocol rather than the underlying algorithm and the output quality. Moreover, the inherent overhead of secure computation makes it infeasible to run the protocol multiple times with different parameter values and randomness, like in the case of plain text clustering. When the data owners do run a clustering protocol and receive the clusters in their dataset as output, the next challenge is in evaluating the clustering quality. If a data owner evaluates only based on their local dataset, then it doesn't give an accurate picture. In this example, the output quality for the local dataset of each data owner seems to be good, but it's clear that the combined dataset has 4 clusters and not 3. So there is a need to securely evaluate the output quality on the combined dataset, and one way to go about this is to securely compute clustering indices. Now there are 2 aspects to this. The first is extending the protocols to efficiently compute such indices from the output. Secondly, since these indices are computed on the combined dataset, it is important to analyze if outputting it can leak any private information and if there are other methods of evaluation better suited for the privacy preserving case. Finally, since there is an overhead to evaluation and rerunning the clustering protocol multiple times, we would want the protocol to be robust to outliers and handle noise well, especially since it's harder to remove outliers and noisy inputs when the data is distributed. So the plain text scenario makes it easy to select optimal parameter values and evaluate the clustering output, while this is harder in the secure scenario, mainly because of the distributed dataset and the overhead of secure computation. So to summarize, we surveyed around 59 works on secure clustering and found that only 10 were fully private. Our benchmarks show that the runtime of the state of the art among these protocols varies significantly. So improving the efficiency of secure clustering protocols with respect to runtime, communication, and memory consumption is an important research direction. Application of secure clustering in the real world requires designing protocols whose parameters can be set independent of the input data. The protocol should be robust to outliers and noise and should work well on different types of datasets. Finally, practical application requires developing techniques to securely evaluate the clustering output to enable selecting the best one among different runs and across protocols, like in the plain text scenario. So with this, we conclude our talk. Thank you for your attention. These are our references.